This video provides an academic explanation of the surface chemistry and adsorption mechanisms of activated carbon, based on established research findings. Mechanism of activated carbon in pollutant removal. Activated carbon is one of the most widely used adsorbents for environmental purification. Its effectiveness comes from not only its extremely large surface area, but also from the chemical functional groups attached to its surface. Understanding these surface groups is essential to understanding how activated carbon captures and removes contaminants. Activated carbon contains a variety of oxygen and nitrogen-containing functional groups. The most common examples include hydroxyl groups, carboxyl groups, carbonyl groups, and sulfonic acid groups. These surface groups define the acidity, polarity, and charge distribution of the carbon surface. As a result, they strongly influence how different pollutants interact with activated carbon. For organic pollutants, especially aromatic compounds such as benzene and toluene, adsorption occurs mainly through pi-pi interactions. This is because both the aromatic pollutants and the carbon surface have delocalized pi electron systems that attract each other. In addition, hydrogen bonding plays an important role. Functional groups like hydroxyl and carboxyl can form hydrogen bonds with polar organic molecules, allowing activated carbon to capture dyes, alcohols, and other organic contaminants. However, in the presence of moisture, water molecules can compete for these active sites. This competitive adsorption phenomenon can reduce the efficiency of organic pollutant removal. When it comes to heavy metal ions, the mechanism is quite different. Metal ions like lead, copper, and cadmium are positively charged. Activated carbon often contains negatively charged surface groups after oxidation. These groups attract metal ions through electrostatic forces. After this initial attraction, the metal ions form coordination bonds or surface complexes with carboxyl or hydroxyl groups. This results in stable adsorption that prevents the ions from re-entering the water. Activated carbon is also used for gas phase pollutant removal, especially for carbon dioxide and volatile organic compounds. Oxygen-containing functional groups increase the affinity of the carbon surface for carbon dioxide molecules. Polar functional groups also help capture various gas phase pollutants. However, as with organic removal, the presence of moisture can reduce gas adsorption efficiency because water occupies active sites on the surface. To improve performance, the surface chemistry of activated carbon can be intentionally modified. Oxidation treatments using nitric acid or hydrogen peroxide increase the number of oxygen-containing groups such as carboxyl and hydroxyl groups. This enhances interactions with heavy metals and polar pollutants. Nitrogen doping introduces nitrogen-containing groups into the carbon framework. This improves pi-pi interactions and increases selectivity toward nonpolar organic molecules. Despite these benefits, excessive or aggressive surface modification can damage the pore structure, reducing the overall adsorption capacity. Therefore, achieving a balance between functional group introduction and pore preservation is essential. Overall, the adsorption behavior of activated carbon is determined by the combination of its porous structure and its surface chemical functional groups. By tailoring these functional groups, activated carbon can be designed for more selective and efficient removal of heavy metals, organic pollutants, or gas molecules. This makes activated carbon a highly versatile and functionally engineered adsorbent with great potential for future environmental and industrial applications.